Thanks for having me back again. Today I have this mouthful of a topic, building an asynchronous experience with building a synchronous experience with asynchronous data. It went wrong already, like in the beginning. It'll all make sense by the end of the talk, I do promise. I'm Tuomas. I'm the co-founder and CTO of Liner. I've been working on sync engines for way too long. Since 2004, I need to stop. Hopefully, I'm done, after the next few years, and I can, spend my time on something else. But if you don't know Liner and what Liner is a project management system used by most startups, very many growth companies, and even quite a few enterprise companies. And I've been talking about the sync engine quite a few times already. It seems that a new episode drops every year. I started talking about the Liner sync engine 4 years ago. Gave a talk on how we've implemented it. If you want to sort of go through the talks, they're pretty much in order. The first one was about the intricate details of the sync engine. The second one was about how we scaled it for larger workspaces. And then last year I talked about how the unexpected benefits that came from local first, or the synchronization engine, which were one of the points that I said there was that we didn't anticipate for our developer experience to be up-leveled by that much. And I want to dive deeper into this one aspect of our synchronization engine and sort of the story of Liner so far, and how we maybe through sort of randomness and good luck, found an API that really works for us and keeps our engineers moving very fast and be able to ship features as quickly as we do. So we need to go a bit back in time, and when we started Liner, we put in a synchronization engine very early on. Literally the first thing that I wrote 6.5 years ago now was a synchronization engine, and we thought about what kind of API do we want to access the data in our application with? And we started off very simply, as you do as a startup. You try to cut corners, you try to make everything very simple, and we ended up with a model that we knew wouldn't scale, but we knew that it would get us running and be able to service our customers for the next few years at least, which was to load up everything into memory. So we effectively said, what should our data look like? If you have everything in memory, rendering becomes pretty trivial. It's effectively, React, you take the state, and the UI is a function of that state. So if you have everything in memory, we can render the UI very, very simply. So we started off with this, workspace model object that we have on top. And that has a few arrays. Obviously, it has an arrays of teams and an arrays of user. We modeled these not as arrays. We sort of foreshadowed the need to have something in between, to have an abstraction layer, and we call them collections. They're effectively an instance of a collection type that looks like an array, but you cannot access the underlying array directly, but you have to go through some methods on that collection in order to access the individual model items within there. So you've got this workspace object. It has a property called teams. It has a property called users, and those are collections where you can access the teams and the users of that workspace with. Going further, a team will have labels, it will have issues, it will have states, and a state is effectively just a state that an issue can be in. It can be, planned, or it can be in progress, or can be canceled, or whatever that is. So again, a team will have properties pointing to collections that will hold other model objects. And if you go further from there, an issue will have comments, again, accessible through a property called comments, which is a collection of comments associated with that issue. And it will have history items. So what has happened to that item? Anything that we want to display in the UI. And lastly, on the other side, a user will have favorites and notifications as well. This is not the whole tree that we had in the beginning, but to give you an example of, this is how we started out to model the object. Currently, we have probably 95 or even 100 different kind of model objects in Liner, so it has grown quite a bit, but humble beginnings. We quickly realized that it wasn't a nice tree like this, but it was effectively a graph. So we had pointers going across. An issue will have an assignee, for example, who's supposed to work on this thing. And so an issue will get a property called assignee, and will just simply reference a user. And that was implemented as, effectively a simple reference. You have an issue, it will have a property, and that will be pointing to a user. the user will need to be able to list all the issues that are assigned to a user. So we'll add a collection called issues on the user, pointing back to any issues that are assigned to the user. Going further from there, an issue will be pointing to a state. A state will also have a collection of issues, like if you want to know how many in-progress issues there are in a specific state, you can access the collection and get to the issues that way. And so on and so forth. You can have a label associated with an issue. The difference there is that you can have many-to-many relationships, like one issue can have multiple labels, one label can have multiple issues. So you've got collections pointing both ways. You've got issues, you've got labels. And same goes for comments, and then lastly, sort of favorites. The comment is interesting in the way that sort of it points to itself. So we don't have a acyclical graph, like everything's just a big blob of stuff, and we need to somehow reconcile this graph as well. And then on the favorite parts, like we also have like simple references to objects. A favorite will point to an issue, but an issue doesn't need to point back to favorites, because we don't really care about all the favorites that an issue is part of. So simply we have what we call a reference from a favorite to an issue. So you can access it through that graph. So we have effectively 5 different ways of managing our data. And reference types. We've got one-to-many, many-to-one, many-to-many, one-to-one, and reference. One-to-one is actually not described in this example here, but like you can think about reasons where you would have one-to-one relationships between different model objects. And to simplify things very much, you can go to the other talks that I've given around the sync engine. The responsibility of the sync engine is to keep this object graph in memory synchronized. Whenever any updates happen, whenever the user comes back, the sync engine will do its thing, and it will construct this graph in memory, hook up all the different properties to each other, put items in the right collections, and give you, as a user, effectively this nice graph of pure synchronous in-memory data that you can then use to render your views. And with React, this becomes quite simple. You have effectively a view or components that will be passed on model objects, and then you start rendering them. So if you jump quickly into looking what that would look like, if you want to render the sidebar, for example, all the team listings and their associated navigation elements, you simply take the workspaces model instance that is handed down to the application from the top, and you take teams, which will be a pointer to a collection of teams, and you iterate over it. You either map or you do a for each loop over them, whatever you do, and you pass that team into a collection representing each of these teams. And for each of the teams, you go deeper. You go into just properties of that team object. You say, let me sort of render the icon of the team or the name or the key in order to construct the URL to get me to that team when I click it. So it's simple React. There's nothing particularly interesting about this. And the same thing happens for all kinds of other things as well. There's some interesting nuances, for example, in the inbox up there, where we go through a workspace to the current user, which is effectively helper property that will just simply look up your user in the users collection. You go into that notifications collection, and you look at the length of that collection, which you can do because it sort of is a stand-in for an array. And then you can print out how many items you have in your inbox. On the right-hand side, we're rendering the issue list in effectively the same manner. We loop over the states of a team, and for each state, we loop through the issues in that team. Again, just by going through collections and accessing properties. And same goes for one particular row. We just are handed down an issue model object, and then we loop over and represent that object. This is our trivial. This is what you do with React. One more thing, we have effectively all of our view state in that same tree as well. So if you have that that top right-hand corner button that brings out the side panel, that is effectively just the user setting, sitting in a settings model object associated with the user. And if you want to toggle that sidebar, you just toggle its value, and the UI will follow. The beauty with this is that because the synchronization engine sort of handles updating the tree, of the model representation in memory, and we use mobx to bind ourselves to that tree. Whenever any of that data updates, we are guaranteed by this reactive framework, mobx, you could use whatever you want, that your UI will get updated as well. So effectively, creating an application and building new features becomes trivial. It becomes defining the data that you want to use or the schema for that data, and then rendering it. And that's it, you're done with a new feature. So again, we had these 5 different relationships, and we defined like how we want to access them. What do we use in order to access things in a one-to-many reference? And that's a collection. On the other side, if you have a many-to-one reference, it's simply just a pure JavaScript reference, a pointer to an object, which you can then access. And everything is fully, nicely synchronous. And this was sort of the API that we used for the first 2 years, and we were super happy, and it let us move us very, very quickly. And I do remember like the best Friday was one where I sort of shipped like 4 medium-sized features in one day, just by utilizing this, like defining a data model, building the UI, and then shipping it. And it worked nicely until we hit approximately 50,000 objects within linear. And we knew that this was going to happen. We knew that we were constrained on loading everything into memory. And if you load up 20,000, 30,000 issues or model objects into memory at startup time, it takes a bit of time. At 50,000, we felt that the user experience wasn't great anymore. Today, if you have a sort of modern computer, it probably takes you like 800 milliseconds and maybe a second to load up 50,000 model objects, which is sort of fine, but we want to be faster than that, and we want to support way more objects than 50,000. So we had to figure out a way of making our data access asynchronous. But we sort of did not want to give up on the notion of synchronous data access, because that was the way that you built React applications, and that was the way that we enjoyed building applications. And Aaron said this morning, if only you could write queries. I want to sort of go a level above that, and I think there's an abstraction on top of that we can implement in libraries, which is that the queries themselves are actually implementation details. And what you can have is simply this data access layer, where you have a graph in memory that is at the same time synchronous, but also asynchronous in nature. So what did we do? We had this tree of stuff, and it was becoming too big for our customers, so we had to do something, and we looked at the model, and we're like, well, you have only one workspace, you have a few teams, you have a few users. Those are probably fine to load up into memory, but it's the issues and it's the comments and the history that needs to go, because those are the bulk of all the objects that you have in an application, or that you have in linear, and we want to load those asynchronously when needed. We don't want to spend the time to load them up into memory at the load of the application. What it then meant for sort of our instances of access was, we had already this collection object or instance or class in place for any of the references that were, one-to-many. We just simply made that a lazy collection. And what I mean by that is, if you accessed, for example, the teams of a workspace, it was still a collection, and you would simply get the collections back because they were loaded already into memory, and there would be nothing that happened there. Same goes for if you access the users or continued accessing users of the workspace, you would get all the users back through that collection immediately without any asynchronous actions. But what will happen if you went to a team and you wanted to render all the issues? The issues weren't loaded into memory. Well, a collection can also be empty. So that's what we started off with. We were like, can we do something where we take that notion that the user wants to access the issues of a specific team and just return them an empty array saying, oh, it's empty, and then maybe 10 milliseconds or 100 milliseconds later, populate that array and say like, oh, they were here actually all together. So effectively handing off the responsibility to mobx to re-render any UIs that were accessing those issues. And that's what we did as a first trial. And it actually worked out pretty nicely. We had a few problems with it, and we sort of uncovered those. But the idea was to come up with an API, and this is sort of the API of a collection. You access the issues through the team, you get a lazy collection back, and the moment you access any of these methods and If these methods look familiar, they're effectively just the methods of an array, because we wanted to mimic sort of the API of an array. If you access the elements of the issues, and that's the one that we added, which gives you a raw array back of those issues, or if you access the length, or you mapped over them, or you filtered, or you found, or did a loop over every on that issues collection, it would be a hint for the sync engine to start hydrating that collection. It would immediately return, so it would be a synchronous call and be like, well, there's nothing here, empty array. Or if you try to find something, well, you didn't find anything. But it would kick off this hydration in the back end, and we would try to fetch those issues from local disk. And very quickly thereafter, we would populate that array, reaction would fire off, and your UI would be re-rendered. And therefore, effectively our API stayed synchronous. We could just do issue.elements map and render out any kind of JSX that we wanted out of it. So it worked out pretty nicely. Like, you would first get a view without any issues, and then very quickly later, it would flash and your issues would appear in there. However, we had a small problem, which effectively was that if you have an empty array, we sort of want to render something different. Like, if you have an empty team, we want to give you the splash of saying, well, we want to describe what that view is about, and we want to give you the ability to create a new issue, which was in conflict with sort of this notion of like handing you back an empty array, which meant that we would think that the team is empty, we would render this view, and then a moment later we would switch back to this view, which would include a lot of flashes, and the UI would just not be very nice. So we wanted to hand engineers tools to make this better and make the user experience much nicer. And what we did is we utilized React suspense boundaries. If you haven't used suspense boundaries before, it's effectively a way of making React synchronous from an asynchronous nature. In any point in time, if your UI rendered code throws out a promise, it will bubble up to the topmost or the next suspense boundary, and it can render a fallback until that promise resolves. The idea there is that if any of your code is asynchronous in nature, you can throw out your promises, and that promise will be caught. Some loading screen will be rendered while the promise is resolving, and once the promise is resolved, it will just re-render everything, and because the promise is resolved, you can now render your UI perfectly. So we added two new methods, or two new things to the access on our collections. We said, you can call hydrate explicitly on the collection, which will return you a promise if, well, it will return you a promise. And the promise might be resolved already if we've previously hydrated all the issues, or it might be a promise that is in flight because we load things up from disk. And then we have this helper function called resolve promise, which is super simple. It will return you the result if the promise is resolved, or it will throw that promise to react to the next suspense boundary if it isn't. So this is our way of gating and hitting effectively suspense boundaries if we try to access data that is asynchronous in nature and that we haven't loaded up yet. And with this, we were able to effectively put a suspense boundary around our issue list, and you would get sort of this flasher, this cursor that we have for a loading symbol while we're loading things up from the local database. And once that load was complete, then we would render the issue list, or then the fallback of that splash screen if there really are no issues there. So it's a way for us to make sure that we can hydrate things before we actually try rendering out anything. Well, the next problem that we had, this works nicely for collections, that it was super easy to implement. Everything was still nicely synchronous in nature. But how about these direct references? Like if you point from a favorite to an issue, and now suddenly your issues aren't actually loaded into memory anymore, like that's a JavaScript pointer. If you try to access it, you will get undefined, and your code will crash because we disregard the type on that property, and you try to access properties of undefined, and you run into problems. And we did effectively the same thing, which is replaced these references with lazy references, which was a bit of a bigger operation that we had to undergo, where we said that instead of having pointers, we put an intermediate object in between any pointers that point to lazy objects that we load from disk later on. And the interface was somewhat similar. So if you have a direct reference, it's just simply comment that issue, you will get that particular issue back. And comment always has an issue. So there's no optionality here. Like, it needs to be fulfilled. There cannot be a comment that is not tied to an issue. With the lazy reference, like if you access comment that issue, you get a lazy reference back. And lazy reference is in fact a promise itself. So you can simply do await issue and resolve promise, which will go down the suspense route and wait for that issue to actually be loaded from disk and then re-render your component, which makes it simple. You need to add this one line in there, and you need to actually get back the return result from the resolved promise, which is resolved into an issue. And then you can simply render that issue title. This worked nicely for React components, but maybe not for sort of, our action codes, like if you go through the command menu, which is effectively imperative code. So what we added to a lazy reference is also the ability to just query its value. So you can do comment.issue.value, and because we're not sort of specifying any resolving of promises, you either get undefined back, like if you haven't loaded it up yet, or you get the issue back. So you need to handle that in two cases, which makes it a bit more complicated, but again, in many cases, you can argue that the issue has been loaded already if you're looking at the issue or the comment, and that made it easier to simplify our code in many places. And lastly, we added a bulk operation of hydrating all these lazy references, because you can imagine issue will have pointers to multiple things that are lazily loaded that we don't have in memory, like projects or project milestones or whatever you can associate with an issue. So we have a helper method that can say, take a comment and just hydrate the comment itself and all the properties that it contains. So if a comment has a lazy reference to anything, we'll make sure to resolve it, and we give you a promise back, which will resolve when all of that operation is done. And what that means is you can then simply access the value of that issue, and it will be there. And the way we do that is we do it obviously at runtime. We have these guarantees that we've loaded up everything before the promise resolves, but we do it also on type, in the type level. So if you call in hydrate on a comment, what you get back is this hydrated comment. And hydrated is effectively just a decorator or a generalization of the comment, and what it will do, it will loop over all the properties in the comment and look at all the lazy references therein and just make sure that the value is now typed as non-optional. The value will be there. So in the end, TypeScript will be happy as well if you've hydrated your things. And this lets you push up the responsibility of hydrating your stuff to the upper layers. Like if you have a component, you just want to render a comment and its issues, you can simply say, well, I need to be passed in a hydrated comment. And then somebody up there needs to sort of be responsible for the hydration. So with this, we had the ability to load up things asynchronously into memory. And obviously, the next big problem was that we cannot have everything locally on disk, but we need to go to the network in many cases. And today, probably like 95% of all the data, still lives on the network and is not even on the local client. And we load it whenever needed. But because we had put this lazy loading in place to load things up from IndexedDB, there was literally nothing we had to do in order to support this network case. So we just simply changed the backend to, instead of directly load from IndexedDB, we put a model loader in place, which will first try to load up any entities from the local cache or local IndexedDB, and if it wasn't found, we would go to the network, make a GraphQL query, load up all that data, put it into IndexedDB, and then return the result. So the next time you came along, you would have all the data in IndexedDB already, and it would be a super fast operation to do, without changing a single line effectively on the front-end side. Instead of being 10 milliseconds or 100 milliseconds, it would now be like half a second or maybe a second to load that data in. But in terms of promises and all the same stuff, it simply worked. So the last thing that we did over the past maybe half a year now is to sort of make the user experience even better. Like we had this notion of eventual consistency in the application where if you accessed any collection or any lazy reference, that was sort of the hint for the client to go on and start loading model objects back. And the problem with that was that if you didn't do anything else in the application, like you would come into this page, for example, of a project, and you would have 20 or so different model objects that would have to be loaded from disk, and they would start popping up. So it was totally fine for you to sort of create an application without thinking about preloading, and it will eventually work. It would load up everything, and in the end, your UI would be nice. But we don't sort of really like flashes or rendering things in gradually. We want a nice, coherent user experience. So the last thing that we did is that we preloaded these models, or gave APIs for our engineers to preload these. And what we did is we used React Router to associate routes with the models that we want to preload, and had a whole API around making sure that you can define what data you need before you display this route. And the beauty of that was that we now had tied a URL to the data that we wanted to load. And we're not doing this when you click on things. No, we're doing it when you sort of intend on clicking. Effectively, if you hover over a link, that's a cue for us to be like, well, you probably are going to click this. Like, there's maybe a 5-millisecond timeout. If you hover on a link for more than 5 milliseconds, we start loading up all the models. So when you click the link, probably everything is already loaded. If not, we can wait for all the data to load, show you a nice loading spinner, and then present the rest of the page in simply one go. So this is how we effectively kept our API very synchronous, with having 95% of our application effectively be asynchronous. Thanks.